So where were we? Where were we? So 1 second. We were talking about a couple of classes of molecules. Still kind of doing this chemistry review, and a little bit on the biological activity. We were on number 6 still, which is reactions, and from the Volhard-Shore book, and the reactions we're kind of highlighting right now are carbonyl reactions, enol and aldol, which is kind of a summary of a whole bunch of stuff we're talking about. But one of the things I want to do, and we're gradually transitioning to pharmacology topics, was we talked about, I introduced the concept of IC50, right? And did anybody have any questions about that, or any of the other topics that you remember from the asynchronous lecture or synchronous lecture? Well, so I'll show. What I want to do is talk about IC50 a little bit more, and like the thing like LD50, and I want to take that a step further because we introduced it, but we didn't really go into much depth. And so when we talked about IC50 of Warfarin, which was the blood thinning drug, the IC50 was equal to about 1 to about 4 micromolar or so, depending on who's measuring it. 1 to 4 micromolar. Do you guys, have you seen IC50 in your courses? I don't know. It's not exactly a biochemistry thing, but it's a little bit more on the pharmacology end. Has anybody ever seen or heard IC50 before? Maybe in research or somewhere else? Does anybody? Does anybody? So nobody can explain it to me, because I can explain it. But does anybody know what I means and what C means? I guess. All right. And actually, IC50 was something that was discussed quite a bit in this seminar just now, the 4 to 5 p.m. seminar. But okay, what is IC50? In a nutshell, it means inhibitory concentration. To give a 50% inhibition. A 50% level of inhibition. So like if we say 1 micromolar or 4 micromolar, basically at that concentration, you have a 50% inhibition. Not 100% inhibition, but it's 50%. And that's generally, it's just a kind of a standard measure of potency, the concept of potency. So if a way to think about that is like if I draw a little graph and I have percent inhibition on the y-axis, produced by a drug or something, and it goes from 0 to 100. So 0% inhibition to 100%. Usually you would want a high level of inhibition. If it's, most drugs you want, well, that's actually not really 100% true. Because sometimes you want to activate an enzyme or a channel protein or some other, kind of protein. But often we want to inhibit it, I guess. All right, so let's just imagine I have 0 nanomolar of drug. 0 nanomolar, would you expect that to have much of an effect? Probably not very much effect, right? And so we might expect 0% inhibition. And then we add maybe 1 nanomolar. And maybe that has a tiny bit of an effect. And then we'll say 10 nanomolar. And then we start kind of ramping up, and then eventually we might get inhibition at 100%, right? Okay, so we'll say 100 nanomolar and maybe 1,000 nanomolar. maybe 10,000 nanomolar. So I'm going logarithmically here. Anyway, the IC50 is basically what concentration you're at for 50% inhibition level. So we just kind of go, and this drug will say may have a, what's the IC50 of this hypothetical drug? Should be maybe 10 nanomolar, assuming we're doing nanomolar scale here. Yes, 10 nanomolar, right? Well, okay, so what's a good IC50? What's a bad IC50? Well, typically you want it to be really nice and low, right? And nanomolar is usually pretty good. If I had a drug that was 10 nanomolar against the protein, I usually are pretty happy with that, because that's a very low concentration. I mean, like if you had 10 nanomolar in your blood, it's like micrograms or less. I mean, it's a very, very small amount of a substance, right? So Warfarin, which is a commercial blood thinning drug, the IC50 is about 1 to 4 micromolar. It's really it's kind of a way up here in terms of the concentration you need to thin your blood is actually pretty high, but it's not a big deal because it's not toxic, right? And it's dirt cheap to make. Remember, Warfarin was made like in a single step, so it's like it's a very cheap drug to make. So if you need a little bit more of the drug, it's not that big of a deal, right? Okay, so and then we also said that for Warfarin, we did mention one of the measures of toxicity is LD50, right? LD50, which is a lethal dose, and there's a lot of ways to measure toxicity without necessarily causing lethality. But one of the measures in pharmacology is an LD50, and they'd basically take a population of mice or rats and dose them and kind of find a lethal dose. And what the reason for that is to see how different that is versus an IC50. And for a drug to be non-toxic, you want the LD50 to be much, much, much higher than the IC50, right? The other thing was for Warfarin, which is a very common drug, people did the measurement and they said it's about 186 mgs per kilogram in a rat and 374 mgs per kilogram in a mouse. So it's a little species dependent, and rats and mice are different in a lot of ways, and of course they're different from humans too. There were lots of other measures of toxicity for a commercial drug like this going through clinical trials, and there's a lot of ones that you can do using cells, measurement of cellular toxicity, and other things that don't necessarily involve a species. Okay, but anyway, the point I want to make is that you can't directly compare these, right? Milligrams per kilogram is not the same as micromolar, right? So it's not a direct comparison. But what I'm going to do is the calculations that allow us to see, compare, basically turn this into micromolar, right? And then you'd see, at least in a rat or mouse, how different the efficacious dose versus the toxic doses. Okay, that's what I want to do. Oh yeah, the 50 here means something different than the 50 here. The 50 here is the 50% inhibition level. 50 here would basically be like the population of a rat or a mouse or something. And okay, so the meaning of 50 is a little different. All right, so let me just go through the calculations and basically convert these into micromolar. And I'll give you the answer real quick, and then we'll do the calculation. So for a rat, the rat LD50 basically will turn into an we'll say a LC50. LC50, what does that mean? that would be essentially the concentration that would cause lethality in a 50% population. And that is about 9,400 micromolar. And then for a mouse, the LC50 is equal to 1,000 or 15,200 micromolar. So that, I mean, based on that, you can kind of see that, you know, this is way, way, way higher than the effective concentration. And that's a good thing, right? Seeing that massive difference. Okay. Okay. So let's do the calculations now. We're still basically on this topic 6, which is reactions as we go through the book. Okay, so let's first do the calculation for LD50 to LC50, and we're going to do this for a rat initially. And okay, so to do this, we're going to take the LD50, which is 186 mgs per kg. And also remember, I mean, you know, that's 186 milligrams per kilogram, but a typical rat is not a kilogram. It's maybe 100 grams or so. So this is 186 is a little misleading. It's not like we'd be giving a rat 186 milligrams of the drug. Okay, but what we can do is first thing to do is just change milligrams to like micromoles, like a unit of molarity, which because we ultimately want micromolar concentration, right? LC50 will be in micromolar. So what we're going to do is use the molecular weight, right? So this is basically Gen Chem 308 milligrams per millimole. Okay. All right. So these cancel out, and then of course we want to go from millimole to micromolar. So it's 1,000 micromoles in 1 millimole. And then that basically gives us 603 micromole per kilogram. So we're still referenced to kilogram. Okay. Now you could kind of figure out what the average mass of a rat is, but what we can do pretty quickly is go from kilograms to basically volume units using the kind of the average volume of blood in a rat, and that's going to get us very quickly to our LC50 because we're going from dose to concentration. And all right, so how do we do that? So this is a case where we just rely on the average blood volume of a rat, and in most rats, the volume of blood is 64 milliliters per kilogram. And this is called the total blood volume. Or TBV, which is every species basically has this. It kind of varies based on your age. Like humans have total blood volume. Pretty much all mammals have a total blood volume, and but for a rat is 64 mils per kg. And so now all we got to do is take our 603 micromole per kilogram, 603 micromole per kg, and now we can just use 64 milliliters, and that basically gives us 9.4 micromole per milliliter. But we need to be normalized to 1,000 milliliters because we want to be moles per liter, right? So because like if we say like 9 micromolar, or you know, our IC50 is 1 micromolar, right? 1 micromolar is equal to 1 micromole per liter, right? So we got to convert this over to liters, and the easy, so it's 9.4 micromoles per milliliter. All we got to do is basically times this by 1,000, and now we got 9,400 micromole per liter, because 1,000 mils is a liter. That's how we basically got this LC50 for a rat. All right. Okay. Good. Now we basically can do the same thing for a mouse. There's 9,400 micromoles per liter, which is basically saying that's equal to 9,400 micromole. Okay. All right. So now we're going to do the same thing for a mouse using the same kind of measure. The only difference is we need a different total blood volume. Okay, so let's do that. So now we're going to do LD50 to LC50 for a mouse. So we're starting with the dose of 374 milligrams per kilogram. And then again, for that the drug's the same. So it's Warfarin, and it's 308 milligrams per millimole, grams per mole or milligrams per millimole, times 1,000 micromole per millimole. Millimole equals 1214 micromole per kilogram. Okay, and so then we just use a different total blood volume for a mouse, which is it's a little bit higher than a rat, but it's normalized by the mass of the mouse. So it's 80 mils per kg per kilogram. Okay, so now all we have to do is basically take the 1214 micromole per kilogram and we use the total blood volume. We get 15.2 micromole per milliliter times 1,000 by 1,000. Okay, and that gives us LC50 equals 1,500 or 15,200, I'm sorry, micromole per liter, which is, of course, the same as micromole. Okay. Okay. All right. So that gives us this ability to kind of convert a dose to a concentration. And of course, that can be done for, well, this is an example of using a lethal dose. So it can also be used for the effective dose or an inhibitory dose. And we can basically kind of go back and forth from concentration to dose. Okay. All right, cool. So nice. And the bottom line is very little expected toxicity, at least from this measure. And also given the differences between a rat and a mouse and a human, which should be receiving warfarin. Okay. All right, so let's see what else. Any questions? Hopefully those calculations are pretty simple. I mean, it's basically unit conversion from Gen Chem, but applied to basic physiological parameters. Okay. All right. Okay. All right, so that was Warfarin. We also started talking about carbonyl, enol, and aldol. One second. We talked about Prozac, fluoxetine, the antidepressant. And one second. That was a C. Fluoxetine. Prozac. We talked a little bit about the biology, a little bit about the chemistry, a little bit about the biology and how SSRI drugs work. Not going to review the whole synthesis, although it was a pretty easy synthesis. The basic idea was taking a ketone like this, which is incredibly cheap, incredibly, like one of the cheapest organic molecules you can buy, beyond like ethanol or methanol or something. This is a very cheap compound. But the basic idea was they did a little bit of synthesis, and they got the final product, fluoxetine, which was this molecule, right? And they kind of did that by sort of they did that thing called a manic reaction, which sort of allowed them to attach the right piece. And then they did, anybody remember the funny abbreviation or acronym to attach the benzene? It was in the asymmetric lecture. Anybody say it? Know it? This is the manic reaction. Essentially, there were a couple steps. So how was the benzene attached? 4 letters. It was in the lecture. It was Snar. Snar. S-N-A-R. Snar was the method to basically attach the oxygen to the benzene. All right. And yeah, so that was all kind of in the, I think, the asymmetric component of the lecture. All right. So I guess and we talked about how these work. They're reuptake, serotonin reuptake inhibitors. Is this a chiral molecule? Yes or no? Yep, it's definitely chiral. I mean, it's easy to see it. It's the, there it is. It's the chiral center, right? Yeah. And we often identify chirality with a little star or asterisk or something. And so we can call this plus minus fluoxetine. Plus minus fluoxetine. The plus minus refers to racemic. So you're basically making a mixture of the 2 enantiomers. All right, we cool with that? All right. So that kind of begs the question, could one enantiomer be more active than the other enantiomer? We already talked about this for other drugs, like I think omeprazole, which was the proton pump inhibitor. And that was the omeprazole was the weird one that had the sulfur, the sulfoxide enantiomers, right? Well, this is a carbon enantiomer, and but there's kind of like 2 questions. One is could the Stereocenter affect potency, right? Could the Stereocenter affect potency? Well, that's a good question. I mean, If it would, then you could potentially make the single enantiomer, right? Like plus minus really means a mixture of R and S, right? We'll show that in a second. But could you make the pure R fluoxetine or the pure S fluoxetine and maybe obtain an increased potency, right? That's kind of that's a reasonable question. Any chiral drug, you have that issue, right? And sometimes it doesn't matter, or like it's not that big of a deal, and it's just cheaper to make. This is an incredibly cheap synthesis, right? So you'd have to have a very substantial effect on potency in order to really make it worth your while. Make it worth your while to go out of your way, right? You have to bend over backwards a little bit to make a single enantiomer. But we're going to show how to do it because it's fun and it's actually pretty easy chemistry. It's pretty easy chemistry. It's a little bit beyond the Volhard-Shore book, but it's not. It's just one reaction almost. So, okay. So what could the stereo affect potency? And the other question, I mean, and this is, I mean, sadly, the way drug companies work would be like, could a company potentially regain a patent by marketing a single enantiomer? Well, I mean, that's they kind of did that with omeprazole, right? They make that thing called Asymmetric, which is the S stereocenter of omeprazole, and then they sell it, but it's not, you know, the efficacies are pretty similar. I mean, with fancy marketing, sometimes people can claim it's a little more efficacious, but I mean, that's well, it's a sad aspect of drug discovery, that because this is a generic drug, right? And if a drug company could potentially, you know, discover that a single enantiomer is more active, then they could make it, you know, billions and billions of dollars. So it's kind of like a commercial aspect, right? Anyway, those are a couple of the questions. Obviously, another question for us is, how do you make it? How do you make RNS? How to make R versus S fluoxetine? Especially, can we do this using our simple organic 2 knowledge? Can we do it with the simple knowledge you learned in undergrad organic 2? The answer to that is not quite, but it's not that bad, and I'll show you it. It's just an extra reaction you haven't learned yet. All right. So let's talk about how you'd make a single enantiomer of this. All right. Okay. So okay, and going back to omeprazole, which again is omeprazole was that weird thing that had the sulfur, or the chiral sulfoxide. I'm not going to draw the molecule, but it had like something like that, and we had a magic way to make it with a single enantiomer of the sulfoxide, right? What they need to do this reaction or this conversion, or to make this is they need a way to set the stereocenter, like create the stereocenter to be specifically R, or create the stereocenter to be specifically S. It turns out it's not that easy if you use this route, the ketone to the manic and the Snar reactions. It was not. They basically have to change the synthesis. So we'll say that we're going to use a different strategy. That's all I'm trying to say. Different strategy. It's not that different, and it works. It's just a little different. And okay, so here's a question for you. Quiz back from when we talked about these sulfoxides. Do you remember what the types of reactions are called that create a single enantiomer? Anybody remember the word? It's a weird word, enantio something. Like a reaction that creates a single enantiomer. Anybody know? Okay, so you probably forgot it, but if you look back at your notes for this, I told you the word, and we're going to use an enantioselective reaction. Enantioselective. That's the word, enantioselective, and that means it's a reaction that gives us a single stereoisomer, right? It gives us R, it gives us S. Okay. Okay, so they're going to use a different strategy. They're going to use an enantioselective reaction to give them a single stereocenter, which is super cool. This happens to be a Nobel Prize winning reaction. So the reaction we're going to use won somebody the Nobel Prize because enantioselective reactions are like kind of the top of like the most exciting kind of new developments in organic chemistry, right? Really fancy enantioselective reactions. Like if you guys create your own enantioselective reaction, you might get a Nobel Prize, right? Like this reaction we're going to talk about. The reaction we're going to talk about is called the Sharpless Asymmetric Epoxidation, or SAE. Okay. And so this was the Sharpless asymmetric epoxidation reaction won the Nobel Prize, I think in, when was it? 2001. 2001. Professor Barry Sharpless, his name is Barry Sharpless. I think he's at maybe Caltech, he won the Nobel Prize for discovering this fancy reaction that basically creates epoxides. What's an epoxide? It's this, right? Epoxides asymmetrically, very nicely. Okay. All right. So what is this new cool route? And let's review also, how do you make an epoxide like using your plain old organic reactions? So like if I had I want to make this epoxide, boring old epoxide. You guys know how I'd make this boring epoxide using your organic 2 knowledge, your long forgotten organic 2 knowledge. Anybody know the reagent? It is a 5-letter abbreviation. Somebody said with a diol. With a diol, yes, you can make an epoxide from a diol. Yes, you can take 2 alcohols. Yes, you can do that. That's not, I would say, the best way to make an epoxide. I think the best, most direct way to make an epoxide is from an alkene. And it's using an organic 2 reaction with a 5-letter abbreviation that begins with M. Anybody know that the M something reagent? This is Volhard-Shore 9, chapter 9. It was MCPBA. You may or may not remember that. It's just a cool way to make an epoxide, right? Okay. And it's I'm not going to do the mechanism, but basically this molecule MCPBA it has an extra oxygen, and the oxygen just gets snapped in there. Basically, that's it. It's a cool reaction. And why is an epoxide cool as a synthetic thing, right? You can make this thing, but it looks a little silly. And what could you potentially do with it? Well, you could react it with a nucleophile. One of the main things you do with an epoxide is open it up. Then you throw in a nucleophile and it opens it up. All right. And then the nucleophile opens this up and you get an alcohol, right? So that's a review of kind of what an epoxide does. All right. All right. So we're cool with that. And we can use this as a way to build a molecule. And that's what they're going to do. The only difference is we're going to use this fancy way to make the epoxide and give us a single isomer, single stereoisomer. Okay, cool. Let's do it. Let's do it now. All right. All right, so still no number 6 reaction, carbonyl enol aldol for the most part. Okay, so we're going to make S Prozac. And by S Prozac, I mean a single enantiomer of Prozac. All right. So this is how they do this. This is I don't know if it's Eli Lilly that did this, but it's one of the literature procedures. I don't actually have the reference in front of me. I could find it though. All right. So to make the single enantiomer of Prozac, they start with this chemical. All right, so this is an alkene and it's got an alcohol. In order to do this, well, let me show you the fancy reaction, the Nobel Prize winning reaction. This is the SAE reaction: Sharpless, asymmetric, epoxidation. They use a chemical called minus DIPT. I'll show what that is in a second. They use this peroxide. It's a tert-butyl, oxygen tert-butyl. This is all just part of the recipe of the SAE reaction. They use titanium. Titanium, it's a metal. IPR4. Those are isopropyl groups. So it's titanium with 4 isopropyls and oxygens, right? Okay, this magically creates an epoxide. As a single enantiomer. Okay. And let's just go back real quickly to my last page, just real quickly. To be clear, MCPBA doesn't do that. I mean, MCPBA makes a racemic mixture, right? This is plus minus. This molecule is a racemic mixture because MCPBA doesn't have anything that would direct where the oxygen is going to be. The oxygen is coming towards us, the oxygen is going away from us. It's basically a racemic mixture, a 50-50 mixture, right? But here, this is not, this little recipe here creates a single enantiomer of the epoxide. And that's, again, it's the come up with a cool reaction like this and you are a Nobel Prize winner, potentially, right? Okay, all right. Certainly in 2001, if you came up with a reaction like this, you'd be a Nobel Prize winner. Okay, so, and of course, where are we going with this? The final product is a few steps away. I'll draw that down here. Because we still got a couple steps. It's not that many steps though. And they do it very efficiently. That's S-fluoxetine or S Prozac. All right, so you can see some of the molecules there, including the chiral center that we need to be S. And is this S? Do you guys, do you remember how to do S and R? How do you do it? You assign the priorities. I think this is A. Let me get my blue. The oxygen's A. The D substituent is probably the H. There's your D substituent. And then between phenyl and the CH2 group, the phenyl is probably the B and the CH2 is the C. Okay, because the oxygen wins because of the atomic number. That's oxygen higher than carbon. D has a really low atomic number, so A and D make sense. B has the double bonds, C does not. So I use my thumb method. So with my left hand, I point down towards where that D is, and then my fingers wrap from A to B to C, A, B, C, right? A, B, C. And that's how I get S. Left hand is S, left hand is S. But if this works with my right hand, then it's R, right? That's how I get S, Prozac. All right, okay, so that's, yeah, we did that, I think, a little bit in the, we talked about stereochemistry earlier. All right, so what do we have to do? What do we have to do? So we got to attach the nitrogen, right? Got to get the nitrogen thing on, we got to attach the benzene, essentially. That's basically what we got to do. All right, so how are we going to do this? Finish this synthesis very quickly. And also we have our chiral center, right? We have that chiral center right there that we need, the S chiral center, right? But we don't need this bond to oxygen, right? This bond to oxygen is silly. It's not part of our product, right? So the first thing they do is they delete that bond. They say lithium aluminum hydride, which is just a reducing agent, and it's H dot minus, right? H dot minus. Essentially, lithium aluminum hydride is H dot minus, right? Okay, and we can just delete the bond and turn it into an alcohol. So attack. All right, now we got an alcohol. So now the epoxide gets turned into an alcohol, and then that's kind of closer to what we want. So now we got an alcohol, right? You can see now that's definitely on track to where we want to be, right? So next they want to put the nitrogen on. And so the way they do that is they turn the right alcohol into a leaving group, mesyl, MS, mesyl, M-E-S-Y-L. It's one of the nice leaving groups. It's kind of like a chlorine, or making a chloride or something like that. But mesyl they can do selectively on just the primary and not the secondary. Because why? Okay, so what's the product? We'll think about this. Why could they turn, why would this work? Why would it work on just the primary alcohol and not the secondary alcohol? Any guesses? And it basically just attacks, takes out the chlorine. Well, the reason is because this primary side is less hindered. It's less, sorry, one second. It's the primary side, the right side, it has less stuff around it. So it's less congested. So this primary side is more likely to react than the secondary one. That's why this guy reacts, not this one. All right, so cool. That's great. Well, now to attach the N-methyl, all we got to do is throw in methylamine, right? And it's a nucleophile. It's a nucleophile that'll kick off the leaving group. So that's easy. See, it's pretty fast. Not a hard synthesis. They just use methylamine, H3CNH2, which is essentially that, right? And that just kicks off the leaving group. That was easy. Look at that, we're almost done. And at this point, they actually just do the Snar reaction that we used in the other synthesis. So the Snar reaction attaches the benzene to the alcohol. And that reagent was NaH, super strong base, takes out the proton. And then they bromo, this is Snar. And we talked about that in the asymmetric lecture. So yeah, in a nutshell, base takes proton, makes O minus. O minus attacks this benzene. And connects to it, and the CF3 allows that all to happen because there's a little bit of a charge moving around the benzene, and the CF3 stabilizes that off. But anyway, it all falls apart, and you get the product. Okay, cool. So we made S-fluoxetine or S-Prozac through a pretty clever route that uses the 2001 Nobel Prize, basically the reaction that Sharpless discovered, SAE. Okay, so what are the obvious questions? Like, what's minus dipped? What's minus dipped? What does the minus mean about dipped? Minus probably means something, right? What does minus mean? Does it mean it's chiral or achiral? So usually minus or plus means it's chiral, right? So this is some kind of chiral molecule. And that's why, I mean, in order to create chirality in a chiral center, you need to translate chirality from somewhere else. Like if I didn't have dipped in there, say I just did this, no dipped. I'm trying to cover it up. If I didn't have that top reagent, how could I possibly create a chiral center? Because there's no way I could get it, you know, the oxygen could be directed to be in the front. This thing kind of directs the chirality to be coming towards us, okay? So dipped, what's dipped? Minus dipped is this molecule. It's about 25 grams for $30, which is actually pretty cheap for a chiral molecule, pretty cheap. And the other thing is it's catalytic. So it's not like you're even using a ton of it. You're just adding a little sprinkle to get this crazy reaction to go. So this is catalytic. Being catalytic, I mean, you're using very little of this chiral substance. That's part of the reason that Sharpless won the Nobel Prize, because he got the reaction to work with a catalytic chiral thing. Okay, all right. Okay, so if we wanted to, we're making S-Prozac. How would we make our Prozac? So if we, oh, sorry, there it is. How would we make our Prozac, which would be the enantiomer? And somebody said, yeah, just use plus dipped. That's right. All you got to use is plus dipped. Use the, if minus dipped leads to the S enantiomer, then plus dipped, which would just be the 2 hydroxys going away, right? That would, plus dipped would basically push all the way forward, and then you get our Prozac, and the oxygen would go in the back. Yeah, that's pretty logical. Just use plus dipped. Does anybody know what dipped is derived from? What natural product? It looks like this. Anybody know what that molecule is? Dipped. And what does the T stand for? Anybody know? T. Here and there you learn little molecules that are, these are actually common molecules in our common lives. T is tartaric acid. Tartaric acid. Tartaric acid is found in wine. It's a very simple natural chiral molecule that's dirt cheap. So it's a chiral dirt cheap molecule. And those are the best kind of molecules for a reaction like this. It's dirt cheap. It's very abundant on the planet. It's not, you know, you can derive it from natural sources basically. And then all they do is it's not just tartaric acid, right? Tartaric acid would be, or minus tartaric acid, would be the dicarboxylic acid, right? Acid. But they make the diisopropyl ester. So there's ester, and that's just kind of, that helps in the reaction. So these ester groups aid in the solubility. How this all works is, there's a little bit more to discuss. I'm not going to do that though. But essentially the Lewis acid probably interacts with the 2 hydroxy groups, and it creates a little chiral cavity, almost like a little chiral pocket. And that allows, that basically will direct the oxygen to attack on the front, in a nutshell. I mean, there's a little more complexity to that, but yeah, that's pretty much how the Sharpless asymmetric epoxidation works. And this is a cool application to create S Prozac. All right, so then the big question is, now we can make S Prozac, but now we can make R Prozac. So, oh yeah, there is one more way you could do it potentially. You use plus dipped, but I could also imagine I could probably invert alcohol if I wanted to. There's ways to do that. I could actually turn the alcohol from towards us to away. There's ways to do that. People probably have done that. I don't know. It's pretty easy to use plus dipped. The only issue is you got to do the whole synthesis all over again. So if you did make this in ton quantities, it'd be kind of cool to just very quickly get to 2 steps away to the to R Prozac also. That is another option. Okay. All right. So yes, it is possible to invert the stereochemistry of an alcohol. All right. Cool. All right. So now we got a big bottle of R Prozac. We have a big bottle of S Prozac. What's the next step? You would determine potency, right? And say, is R Prozac more or less potent than S Prozac? Well, it turns out that in the end, they're pretty similar. So we went through all this trouble. R Prozac and S Prozac are similar potency. Well, that kind of sucks. I mean, if your goal was to make maybe a better drug, or potentially, make $1 billion by creating something that's much better, then this didn't actually work out. However, there is something interesting. So S is a little better. It's like maybe 1.5 times more potent. So a little bit, but that's not, if it's 10 times more potent, that'd be another thing. So S is about 1.5 times more potent. Is that good enough to start a whole new, drug with clinical trials and everything, in order to try to, create a new patented drug that's not generic? Not really, but there is something else that's interesting. So, however, there is another aspect. The S Prozac, in addition to being a little bit more potent, it's metabolite. So all these molecules are metabolized, right? The metabolite from S Prozac is much better, is much more potent, than the metabolite for the R Prozac. So there's like, I'll show that on the next page. But basically, the metabolism of Prozac is that the methyl group gets lost. When we'll go way into depth on metabolism much later in the course, but a common route of metabolism is things like a methyl, N-methyl, O-methyl, things like that will actually get metabolized off, so they'll fall off. And then that happens to be the metabolite for based on S Prozac is actually, I think it's something like 10 or 20 times more potent than the metabolite for R Prozac. So that would actually be a reason to maybe market a new drug, right? So let's talk about that a little bit more. Okay, so we're still on number 6. Slowly getting through this. Reactions, saying carbonyl, aldol. Okay, so let's talk about what I was talking, the metabolism of Prozac. Prozac. And we're going to go back to the racemic drug just to simplify this real quick. So the racemic drug is a mixture of 2 stereoisomers. That's the S1, which we can create enantioselectively. There's also the R1. Okay, so that's the typical Prozac mixture, the racemic Prozac mixture. So it gets metabolized by, anybody remember the enzyme system that metabolizes drugs? A couple letters and a couple numbers. Metabolism in the liver. So pretty much almost all metabolism is with cytochrome P450. So CYP 450. And then there's different isoforms of it. This one is 2D6. So it's the 2D6 isoform. So basically, both of these get metabolized in the liver to the N-demethylated version. So still S, and the R also gets demethylated. And the name of these, that's a dash 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 there on the bottom. Okay, well, first of all, yeah, this mixture is plus minus fluoxetine, which is the racemic mixture. The name of this is plus minus norfluoxetine. Norfluoxetine. And it turns out that the S norfluoxetine is 20 times more active than R, 20 times more active than R. And that would suggest maybe this would be a good thing to market, produce this as a single enantiomer and then create a more potent drug. It comes down to sort of the like, does that really matter? Does 20 more times more active? I mean, you can still make the racemic mixture pretty cheaply, and then still basically get the same effect. So just because it's more potent doesn't necessarily mean it's like worth going crazy on the synthesis. And in the end, the drug company didn't do it. That was kind of an interesting thing. They decided against it. They just decided just market the racemic mixture. Yeah, they Eli Lilly ended up abandoning that. There may be more reasons why they abandoned it. Production of S-fluoxetine. Okay. Other little thing. Here's a good question for you. Why not just take like oral dose of norfluoxetine or like norfluoxetine? Does anybody know why that might not work? Think about that. Well, like why is the methyl actually maybe useful if you're taking this drug orally? Any guesses? Things like a methyl will actually help as it gets absorbed into your stomach. So this might actually be more active once it's in your body, but it'll never get into your body because it's too polar, basically. So oral drug absorption kind of depends on the structure a bit, and a thing like a methyl group can actually help that. So that's probably what the reason is. I think norfluoxetine may still be used, but the absorption of the N-methyl derivative is a little bit better. And generally, the clinical fluoxetine is the most common form is the parent drug with methyl group on it. Anything else I was going to say here? Little other tidbits. Both of these molecules are very slowly excreted. Very slowly excreted. And by kidneys. And the effect that it has is that antidepressant drugs like this, it takes a long time to kind of get it out of your system, and they maybe even weeks to a month. They kind of do this as a slow process where they drop the doses as it actually gradually decreases its concentration. It's also kind of slow to start, and in depression, that's kind of a problem, because I mean, often if somebody's depressed, they sort of need the drug to start working kind of quickly, but kind of due to these molecules being absorbed in your plasma proteins in your blood and things like that, it actually takes a while to get up to a therapeutic concentration, and so it's kind of one of the challenges when doctors prescribe a drug like Prozac, to gradually let the concentration increase, and then if somebody comes off of Prozac, there's a gradual drop in concentration also, due to these molecules just kind of being stuck in your body and also being attached to your plasma proteins in your blood. Okay, all right. Let's see. I think we're basically, I have a new topic, but I'm gonna just do that in the next lecture. I think we're done with Prozac for now. Any last minute questions? I think it is interesting that, well, as a synthetic chemist, I'm always excited to see production of single chiral centers, because that's kind of not trivial. And also, I mean, it's interesting that even doing that, and even with a maybe more active single enantiomer, that wasn't rational. There wasn't enough rationale to do that and make a commercial S-fluoxetine analog. So, yeah, I don't know. Drug companies are a little mysterious. There must have been some kind of strategic discussion, and there may be like other side effects. Maybe the S-fluoxetine has some side effects that the R didn't, or something. And in the end, they just went with a racemic mixture. All right. All right. Are we cool? How are you doing? Any last minute questions on this stuff? All right, I'll see you guys soon. And I haven't looked at the homework yet. I think it was a pretty easy homework assignment. I'm going to try to grade it quickly. Next assignment will either be this Friday or be assigned this Friday or next Friday. All right, see you guys.